Okay, we're in section 15.3, electric fields. Let's get to the PowerPoint. All right. The fascinating thing about both the gravitational and electrostatic forces is they are both capable of acting through space and can produce an effect even when there isn't any physical contact between the objects involved. These are examples of field forces. The most practical way to talk about field forces was developed by Michael Faraday, who lived from 1791 to 1867. In this approach, an electric field is said to exist in the region of space around a charged object. The electric field exerts an electric force on any other charged object within the field. Note that this is different from the Coulomb's law concept of force exerted at a distance, because the force is now exerted by something, the field, that is in the same location as the charged object. The figure on the left shows an object with a small positive charge Q sub 0 placed near a second object with a much larger positive charge Q. The electric field E at the location of a small test charge Q sub 0 is defined as the electric force divided by the test charge. We need for this test charge Q sub 0 to be very small, arbitrarily small, in fact, so it doesn't cause any significant rearrangement of the charge, creating the electric field E, as shown in the figure on the right. Mathematically, the size of the test charge makes no difference. The calculation comes out the same regardless. Okay, when we use a positive test charge, the electric field always has the same direction as the electric force on the test charge. The electric field at point A in the figure on the left is vertical and downward, because at that point a positive test charge would be attracted toward the negatively charged sphere. The figure on the right shows the field due to a positively charged sphere. Once the electric field due to a given arrangement of charges is known at some point, the force on any particle with charge Q placed at that point can be calculated. Notice that Q sub 0 has been replaced by Q, which can be any charge, not just a test charge. As shown in the figures, the direction of E is the direction of the force that acts on a positive test charge Q sub 0 placed in the field. We say that an electric field exists at a point if a test charge at that point is subject to an electric force. Let's consider a point charge Q located at a distance r from a test charge Q sub 0. According to Coulomb's law, the magnitude of the electric force of the charge Q on the test charge is given by the equation here. Q force is equal to K sub E, Q sub 0 divided by r squared. Because the magnitude of the electric field at the position of the test charge is defined as E equals F over Q sub 0, you can see that the magnitude of the electric field due to the charge Q at the position of Q0 can be written as shown here. This E is equal to KE Q over R squared. This equation shows an important property of electric fields that makes them very useful. An electric field at a given point depends only on the charge Q on the object setting up the field and the distance r from the object to a specific point in space. As a result, we can say that an electric field exists at point P whether or not there is a test charge at P. Okay. We can use the superposition principle when we calculate the electric field due to a group of point charges. We first use our equation for the electric field to calculate the electric field produced by each charge individually at a point, and then add the electric fields together as vectors. When you are solving problems, be sure to take advantage of any symmetry of the charge distribution. For example, if equal charges are placed at x equal d and at x equals minus d, the electric field is 0 at the origin by symmetry. In the same way, if the axis has a uniform distribution of positive charge, it can be guessed by symmetry that the electric field points away from the x-axis and is 0 parallel to that axis. Now, here's some problem solving strategies. You can use this strategy when calculating electric forces and fields. Number 1, draw a diagram of the charges in the problem. Number 2, identify the charge of interest, Q, and circle it. Number 3, convert all units to SI with charges in coulombs and distances in meters so as to be consistent with the SI value of the Coulomb constant case of E. Number 4, apply Coulomb's law. For each charge Q, find the electric force on the charge of interest Q. The magnitude of the force can be found using Coulomb's law. The vector direction of the electric field is along the line of the two charges, directed away from Q if the charges have the same sign, toward Q if the charges have the opposite sign. Find the angle theta this vector makes with the positive x-axis. The x component of the electric force exerted by Q on little q will be F cosine theta, and the y component will be F sine theta. Sum all the x components, getting the x component of the resultant electric force. Sum all the y components, getting the y component of the resultant electric force. And finally, use the Pythagorean theorem and trigonometry to find the magnitude and direction of the resultant force if desired. Next, we're going to talk about electric field lines.